Hi everyone, Magnus ShippingLab, thanks for setting this up. I think this is a really great opportunity for us to tell a little bit about what we've been up to. So I'm Jakob, I'm the CEO of a company, a spin-out from the Technical University of Denmark called MASH Energy. And I'll spend the next about 20 minutes telling you about what we're up to in MASH and also what in particular we've been up to in the context of our ShippingLab project. A lot of things have happened, and it's one of those cases where well, things didn't exactly go to plan. I think that happens a lot in these processes, but certainly what we've reached now and where we are now is very, very interesting from a commercial and environmental and a technical standpoint. So I hope you'll get that same impression after having seen my presentation. And then the next part, of course, is getting said presentation on screen, which I will now try to do. There we go. Yeah, so as I said, we're a company called MASH Energy. We're based in Copenhagen, but we're actually an Indo-Danish company. That is, we actually have a daughter company or a subsidiary in India based in Mumbai and also in the city of Ahmedabad. This is something that has been the case from day one, and we consider ourselves a sort of born global company, taking point of departure in whatever the global resources are in terms of delivering on our sort of sustainable solutions. We've, for the past years, been engaged in this very, very exciting project on the ShippingLab called CO2 Negative ISO8217 Biochar. So that's a bit of a mouthful, but I hope the title will make sense after the following pages. So I realize that maybe I'm preaching to the choir here, so I'll be brief. I don't think anyone in this call is not convinced that there is a need for a sustainable transition or a green transition in the shipping sector in general. Today, the emissions from the sector are, I think they're about 3-4% of global CO2 or GHG emissions, but they're expected to rise massively over the coming decades, reaching something like 70% of global GHG emissions, or CO2 emissions, CO2 equivalent emissions by 2050. There's already been regulation put in place on sulfur, on NOx, and of course that's been a bit of a hassle to the industry, but I think the big one has yet to come. And what we're seeing now is there's some proverbial rustling of the leaves from the EU and elsewhere, where you can see that it might be that very soon the shipping sector, at least in the European waters, will be subjected to some significant increase in the restrictions on emissions. So of course, how are we going to handle that? That's the big question. Well, so in MASH Energy, we have one approach to that, which I think is a very good approach. Well, I wouldn't be sitting here if that were not the case. And that is to apply what we consider the unrealized potential of this technological area called thermochemistry. This is actually, the picture here is actually from the Technical University of Denmark, where they have decades of experience with doing research. I believe Joachim will tell you a similar story. There is a veritable treasure trove of technologies out there that could really benefit the world as a whole, but certainly also the shipping sector. What we try to do is say, well, how can we employ or how can we execute on these technologies and produce various sustainable fuels? And forgive me now, because that's where when it gets a little bit geeky, but I'll try to explain to you what this area actually sort of broadly speaking is. Thermochemical technologies are generally characterized by heating stuff up and then control the amount of oxygen that's present in the process. So you might have heard of things such as pyrolysis. You certainly know of burners and heaters and of course combustion engines. A burner or an engine, where in that case you would want 100% of the oxygen to be there, that is sufficient amount to actually combust the hydrocarbons that are put into the process, that is the fuel. But in pyrolysis and in gasification, you actually try to reduce the oxygen content. And the cool thing is that when you do that, really interesting things start happening. And that's sort of the very broad description of what a thermochemical technology is. But in more practical terms, what that means is I can take something. Oh yeah, by the way, so MASH energy essentially has two legs to stand on. We have a lower temperature process, which is very high capacity. That's what I would be spending most of my time talking about in this presentation. But we also have a so-called gasification reactor, which can produce hydrogen and other things at a very competitive cost. What happens is that we take cellulose, lignin, oily fatty acids. It could be many different things. It could be plastics even. So long molecules. And by the way, I'm not a chemist here, so even I don't understand what I put up on screen here. So you're forgiven for not understanding it either. But we take large complex molecules, and in our process, we break them down into smaller stuff. So if you go to less severe processes in terms of temperature, what you'll get are smaller molecules, but they're still somewhat large. You would get, let's say, a bio-oil product. This part of the process, or these processes, are very, very difficult to control because the outputs are very dependent on what you put in, and also the outputs can even vary with just small variations in the process. If you go to higher temperatures, these molecules that you get out will be smaller and smaller. Eventually, you'll actually end up with something like, well, the smallest building blocks that you can imagine. So stuff like hydrogen, but also carbon monoxide, carbon dioxide, and other molecules. Those are, of course, interesting in themselves, but also what's even more interesting is they can start going back and building more complex molecules from this, such as ammonia and methanol. So really what we try to do with our platform is to pave the way for producing these fuels that are highlighted in blue here. And we are already well underway with producing most of these. So that was the very technical part, but really the star of the show, in my opinion, is something completely different, and that's our byproduct. Because whenever MASH produces hydrogen, bio-oil, whatever, we also produce a certain amount of biochar. And biochar, in case you don't know it, is a carbonaceous substance, or a carbon-rich substance that can be used for soil amendment. The cool thing about biochar is that if you consider the contributions of biochar to the overall balance of the let's say fuel plus biochar system, it actually contributes negatively. I'll get back to what that means. Well, by applying this biochar to soils, we're actually sequestering carbon. So 1 ton of biochar will sequester something like, I think that's my next point, something like 3 tons of CO2. And because the biochar cannot be broken down by bacteria, it will actually stay there in the soil for hundreds, if not thousands of years. Another really cool feature of the biochar is that it actually will improve the quality of the soil. That is, soil that otherwise could not be farmed, where forests would not be able to grow. After treating them with biochar, you can actually start growing stuff there. And what is the implication of this? Well, the implication of this is that the platform I just told you about, this very geeky thermochemical platform, can actually achieve CO2 negative fuels. And that is when you're counting the biochar. So that is, of course, in itself a very, very interesting thing, but is this something that has scale to it? And I can tell you very clearly, I have a strong commercial mindset. We would not be doing any of this if it was not something that could scale. Because this biochar can be produced from almost any, or the oil as well, can be produced from almost any biomass residue, biomass waste out there. So if you look at the market right now, and this is sort of the more commercial slide, you can already see a constraint in terms of the current go-to solution for bio-oils, and that would be used cooking oils and derivatives thereof. But also, of course, you have hydrotreated vegetable oils, but even that is a bit constrained because where you get the feedstock for producing the vegetable oil. Then there's this sort of dark horse that has been around for decades, which is the pyrolysis oil. It's a pretty bad product. No one really wants to buy it because it has too much oxygen, high acid numbers, so you can't really trade it at high prices. The good thing about pyrolysis oil, though, is that it has biochar going for it, so that will contribute to the overall footprint of it. So in MASH, what we've done is we've produced what I would argue is the best quality pyrolysis oil that's out there. That is in the raw form, not in the upgraded form, and we've even made an upgraded version that is well, near compliant to most commodity standards of that are used at scale. And the very, very interesting thing about this pyrolysis oil and our sort of future platform is that the volumes that can be produced via these means are significant. They're actually significant to the extent that I believe that it is realistic to say that with some smart application, this could actually power an entire industry. So then there's this project that we did under ShippingLab. Well, basically the idea for that project was to say, well, okay, we have a product here. We have an oil that is very, very close to achieving ISO8217 compliance. There's only a few outstanding spec points that need to be dealt with. So why not partner with some capable companies, DFDS and Alfa Laval, and trying to take this all the way across the finish line? So that's what we did. We applied, we got a project, and we started working on it. And then reality struck, right? So the first challenge we had was to produce a batch of oil for testing, first at Alfa Laval, subsequently on an actual vessel owned by DFDS. And the first thing, of course, was to produce some oil that could go into these test scenarios. At the time when we started the project, we had a pretty simple machine, which, by the way, was part sponsored by the Danish Maritime Fund. I should mention that, which worked pretty well. That's the one that produced this oil that was of good quality. But the thing is that once we started upgrading this machine and increasing the size of it, scaling it up, we inadvertently were changing some of the process parameters. So as you can maybe discern from what I said on a previous slide, temperature is very, very important in these processes. So that means if you change the temperature slightly, even if you're not intending to do so, you will get a very different output. And that's what happened to us. So it actually took us a long, long time to figure out how to get this machine working at full scale. And eventually our machine ended up looking like what you see in the picture here on the right. We did succeed though. And around the end of the year, last year, we produced a batch and sent it off to DK, Denmark. So of course those were good times in MASH, and we were very happy. We were thinking that, well, okay, we just send it to Denmark, engine testing, and then we live happily ever after. I even made a very sort of on our company website, LinkedIn page. I made a very optimistic post. I was struck by the fact that the vessel on which oil was being transported was called the Paris Express, and I had to do a play on words there. That, looking back on it, seems a little bit over optimistic. But what happened then? I'll now be explaining that. Because a couple of months after I made this post, the actual oil arrived in Denmark, and well, we were a couple of weeks away from just doing the full engine testing. We were just doing some last-minute testing to just make sure that, let's say, the oil would not cause any issues in the fuel pumps and so forth. And then, of course, it failed miserably. So these were tests we had not conducted before. We had this weird, you can see these test tubes here, we had this weird polymerization happening where our oil at high pressure would separate out this polymer coating. And also we had some weird phenomena happening when we were blending with paraffinic oils, which we had not seen before because we had primarily been blending with ULSFOs and other more aromatic oils. Anyways, we went back to the drawing board and we actually developed an entirely new upgrading process based on atmospheric distillation and some other stuff that worked pretty well. We arrived at this really, really nice, beautiful product that had, well, it still had some issues. At a time we had some issues with the flashpoint, but we ended up solving that. But of course, we had developed a new process here, but at the same time, that process was not technically viable because it tended to clog up completely. And just as a side point, since then, and actually I'm waiting on the results from Biofuel as we speak. I believe they come in tomorrow. We've changed this process slightly, and we've now shown that we can run it without these issues, these clogging issues occurring. So if those results come in tomorrow, the way I hope they do, and they never do, that's the point, right? If they come in okay, then we have a completely viable process for producing a product that can be used in many, many different contexts. So this is a spec sheet. It's a slightly old one. And what I'd highlight here is, well, it's out of spec, but most of it isn't. And that's in itself a pretty impressive feat, I think. The asset number, we can't really do anything about that. That will always be elevated. This is for our upgraded product, by the way. The water, we have solved that. And then the CCAI, for those of you who know the CCAI metric, you know that it's a bit of a fluffy metric, but it's nevertheless something that is apparent from the ISO 8217 spec. But we're pretty proud of this. We think that this is a good product, and we're trying to get it all the way to the next steps. And the next steps, well, speaking of which, Well, that is in October, I think week 39, we will be testing the fuel in a burner at Alfa Laval. Provided that goes well, we will proceed to test it in a marine four-stroke, the onshore version, or the in-house version that Alfa Laval also has. And then, of course, the final big milestone will be to test it aboard a DFDS vessel for a longer term. So I think I need to round up now. I've probably already spent too much of my time, but in conclusion, you could say that it's pretty apparent here that for you to know what happens, like really validate that a fuel is viable in the maritime sector, you really need to go all the way from well to wake. A lot of learnings will happen literally as you're pumping this oil. Well, we haven't even gotten to that point yet, so I'm worried what will happen, but probably the things will be happening even to the point when you are injecting the oil into an engine. So this is why end-to-end validation is just so crucial. And also because you have an industry which of course is limited by warranties and industry standards that have to be listened to and followed for compliance to be in place. This is something that is the challenge of any fuel producer or sustainable fuel producer like MASH. And well, I only wish there were a platform for this. Well, of course, that's the whole topic of the presentation that I will be giving you a little bit later. So thanks for your time.